Welcome back to the deep dive. Today, we are absolutely rolling up our sleeves because we are tackling a bit of a beast. We're looking at the VMware VSAN Specialist V2 exams, specifically the code 3V0-23.25. And look, if you're listening to this, you're probably already in the trenches.
For sure.
You know that vSAN isn't something you just breeze through by memorizing where the next button is.
It really isn't. This is a specialist level exam. I mean, it assumes you already know how to install the software. It assumes you know what a server is.
Right.
What it's testing is whether you understand the nervous system of virtual storage. Can you design it? Can you troubleshoot it when things go wrong? And can you optimize it?
Right. It feels like the difference between being a mechanic who, changes the oil and the actual engineer who designed the engine block.
That's a great way to put it.
To help us out, we've got a stack of source material here, 10 specific practice scenarios, real exam-style logic, and the architectural reasoning behind them. So our mission today is to deconstruct these.
Yep.
Yeah.
To get at the architecture, the resilience, and really the evolution of vSAN.
We want to move you from just knowing the answer to understanding why it's the right answer.
Exactly.
Yeah.
Because in the exam room, and definitely in a live data center at like 3 in the morning, context is everything. You need to know why you're clicking that button.
Okay, so before we get into the heavy machinery, let's do a quick logistics check. I am sitting down for the 3V0-23.25. What am I in for?
It's a marathon, not a sprint. You have 145 minutes.
Wow, okay. That's nearly 2.5 hours of intense focus.
It is. It's a mental endurance test as much as a technical one. You have to pace yourself.
And you're tackling, what, something like 60 to 70 questions in that time?
That's right. So you have about 2 minutes per question, which it sounds like a lot, but when you're reading a complex paragraph describing a feeling cluster, that time just evaporates.
And the score?
It's on a scale of 100 to 500. Passing is 300. But don't let the numbers fool you. The margin for error can feel pretty tight.
And I noticed in the prep materials, the format isn't just your standard A, B, C, or D.
No, and this is what trips people up. They mix it up. You have to be ready for multiple selection, drag and drop, matching.
All of it.
All of it, plus the standard multiple choice. So you can't just rely on pattern recognition. You actually have to parse the scenario and apply the logic.
Okay, logistics out of the way. Let's dig in. We're going to start with what I call the backbone, the networking and architecture that holds this whole thing together.
A great place to start. If the network isn't right in vSAN, honestly, nothing else is right.
So looking at our first scenario, it's about the requirements for vSAN VM kernel network traffic. The question is basically, what is the absolute non-negotiable requirement?
This is such a classic exam question because it offers distractors that sound, vaguely plausible if you're rushing.
Yeah, I saw one option suggesting it must be routed over the public internet. I mean, can you imagine just sending your storage I/O out over the web?
A security nightmare and a performance disaster. The latency would be insane. Just no.
Another one suggested it needs a dedicated physical hardware appliance. But the correct answer, the one we need to lock in, is that it must have a low latency, high bandwidth connection.
That is the critical phrase. And the why here is so important. You have to think about what is actually traveling through that VM kernel interface.
It's all the storage I/O between the hosts, right?
It is, but it's more than that. It carries everything. The I/O, yes, but also data replication, resyncs after a failure, and all the metadata.
The chatter.
Exactly. The chatter. All the tiny fast pockets that keep the map of the data updated. And if you have high latency, that conversation just slows to a crawl.
So it's like trying to have a conversation on a phone with a 3-second delay. The conversation eventually just falls apart.
Precisely. And if a drive fails and the system needs to rebuild data, that massive flood of resync traffic also goes over this link. If you have a clogged pipe, it's not just slow. The stability of the cluster itself is at risk.
So high latency doesn't just slow down the VMs, it actually extends your window of vulnerability during a failure.
It absolutely does. You want that rebuild to happen as fast as possible. So low latency and high bandwidth are not nice-to-haves, they're the foundation.
Okay, that's the piping. Let's talk about the engine. One of the biggest shifts in vSAN history is next. The difference between ESA Express storage architecture and the older OSA.
A huge topic for the exam. The move from OSA to ESA is a fundamental change. It's like going from a combustion engine to an electric motor.
The question asks for a key performance advantage of ESA. And the answer is something that might surprise people who spent years fine-tuning the old way. It's the elimination of disk groups.
That is the aha moment. For years, admins spent so much time architecting disk groups, matching cache devices to capacity devices.
And 1-to-7 ratio, all that.
A whole science. And if your cache drive failed, the whole group went offline, right? Even the healthy capacity drives behind it were just gone.
A huge blast radius.
A massive single point of failure within the host. ESA gets rid of that completely. It uses a single-tier architecture. It doesn't really distinguish between cache and capacity in the same way. It's all optimized for NVMe.
So by removing that structural overhead of the disk group, what's the actual gain for the application?
You gain huge performance consistency. The source material highlights that this removes that old architectural bottleneck. The system can write to the drives more directly using the full parallelism of NVMe.
And no more of that blast radius problem.
Exactly. Every drive stands on its own.
And that ties perfectly into our next item, which is also about ESA. Let's talk snapshots.
Snapshots. The feature everyone loves to use and hates to manage.
Hates to manage is putting it mildly. The stun times when you delete a snapshot, the consolidation issues. We've all stared at that progress bar at 99%, sweating. So how does this new ESA architecture handle snapshots differently?
It goes right back to that underlying architecture we just mentioned. It uses a log-structured file system.
Okay, explain that. How does being log-structured fix the snapshot stun?
In the old days, snapshots created these long chains of delta disks. The base disk, then delta 1, delta 2, and to read data, the system had to walk that entire chain.
And deleting them meant merging all those files, a huge I/O hit.
A massive I/O hit. But ESA's log-structured file system is different. It doesn't really create chains. It's more like a massive lookup table. When you take a snapshot, it just notes the timestamp in the log. When you delete it, it just updates the metadata table. There's no big data move.
The metadata overhead is just gone.
Drastically reduced. Creation is fast, deletion is fast, and consolidation is practically instant. And, importantly, it's predictable.
That word predictable is key.
It is. So for the exam, remember, ESA equals no disk groups, single-tier NVMe, and log-structured file systems for snapshots.
Okay, let's shift gears. We've talked backbone, we've talked speed, now flexibility and integration. How does vSAN play nice with everything else?
Right, this is where we get into efficiency and resource utilization.
We have a scenario here with VMware Cloud Foundation, or VCF. You've got one cluster that is absolutely bursting at the seams. It's full. And right next to it, maybe in the next rack, another cluster is practically empty.
The classic problem. Stranded capacity. You paid for it, but you can't use it.
So what's the benefit of using HCI mesh here?
It's simple, but so powerful. It lets you share storage capacity across different clusters.
It's like borrowing a cup of sugar from your neighbor, but the sugar is terabytes of NVMe storage.
That's a great analogy. Before HVI mesh, if you ran out of storage space in a cluster, you often had to buy more servers, more compute, just to get the disk slots.
Which is so inefficient. You're buying CPUs you don't even need.
Totally inefficient. HCI mesh decouples that. The full cluster can just mount a data store from the empty cluster remotely. You get to use that stranded capacity.
So if you see a scenario with cluster A is full, cluster B is empty, the light bulb should be HCI mesh.
Absolutely. It's all about busting those silos.
Next up, protocols. The question is, if you're using vSAN file services, what language do the VMs speak?
This is a differentiation question, block versus file.
The options were things like ISCSI, but the correct answer for vSAN file services is NFS, Network File System.
Right. vSAN is natively block storage underneath, but the file services feature sits on top and presents a file share. The protocol for that is NFS. It's not ISCSI. That presents a whole disk. NFS presents a folder.
And why would someone use this instead of just a Windows file server VM?
You could, but vSAN File Services is integrated right into the hypervisor kernel. It's managed in vCenter. It saves you from managing a whole separate OS just to share files.
Speaking of separate, let's talk heavy iron. We have a scenario where a company is moving to VCF, but they have a massive, expensive fiber channel array already installed.
The sunk cost dilemma. The CFO was looking at that array saying, we just paid $1 million for that. You are not throwing it away.
Exactly. So the question is, which feature lets VCF use this external storage?
And the answer is principal storage support for fiber channel.
Wait, so VCF isn't just vSAN only?
That's the preferred path, for sure. But VMware recognizes the reality of the enterprise. The platform supports external fiber channel as principal storage for a workload domain.
That seems like a really important strategic option.
It is. It lets them adopt the automation and lifecycle management of VCF, which is the real value, without abandoning their existing SAN investments. It's a bridge, not a cliff.
All right, let's move on. We've covered speed, we've covered sharing. Now for when things go wrong. resilience, and the worst-case scenario.
This is the most critical part of the exam, in my opinion. This is where you keep your job.
Let's start with a concept that's often misunderstood: slack space. Why do we need to maintain it?
I hear all sorts of guesses. People think it's for log files or OS updates or just general breathing room.
But the source material is very specific. It is strictly for data resynchronization after a failure.
Think about it. If a drive fails, vSAN has to rebuild that lost data somewhere else. It needs free space, empty capacity to write that new copy.
And if your cluster is 100% full, there's nowhere to write?
You're stuck. You're running with reduced redundancy and you can't fix it. So that empty space isn't wasted. It's your maneuvering room during a crisis.
It's the lifeboat. You hope you don't use it, but you don't leave port without it.
That's it. It's operational insurance. And the recommendations are usually around 25 to 30%.
Okay, now let's talk about the referee of the system, the witness host. We've got a 2-node cluster scenario. What does the witness actually do?
The key is what it doesn't do. It does not store VM data.
So none of my actual 100 GB VM is sitting on the witness appliance.
Correct. The witness only holds quorum metadata. Its sole purpose is to act as a tiebreaker during a split brain scenario.
Split brain sounds bad.
It is. Imagine the network cable connecting the 2 nodes gets cut. Both might try to take ownership of the data and run the VMs. You'd get 2 versions of the truth. Corruption.
So the witness is the third vote.
Exactly. Each node checks if it can see the witness.
Yeah.
The one that conforms a majority 2 out of 3 and stays up. The other one shuts down its VMs to protect the data. It decides who's right.
Simple, but vital. Okay, let's define how much failure we can actually take. The acronym FTT, failure to tolerate.
A fundamental concept in storage policies.
The question asks what FTT defines, and the answer is the number of host or disk failures a cluster can survive.
It sounds straightforward, but there's a huge trade-off that the exam expects you to understand.
The trade-off between safety and space.
Exactly. If you want an FTT of 2 to survive 2 simultaneous failures, you need more hosts, and you burn through way more storage capacity.
So it's a dial you have to turn carefully. Higher FTT means you sleep better, but your budget takes a hit.
That's it. It defines your risk appetite versus your budget.
Speaking of risk, let's end with the red alert. The term is degraded.
That is a word you never, ever want to see. That's the 3.0/8 TANIC call.
The question asks, when a vSAN object is degraded, what does it mean?
It's not just a glitch. The answer is a component has failed and cannot be rebuilt.
Cannot be rebuilt. How is that different from reduced availability?
Great question. Reduced availability means a drive failed. You lost a copy, but vSAN is actively rebuilding it or about to. You're vulnerable, but the system's handling it. Degraded means the system tried to heal itself and failed.
And why would it fail?
Usually because there isn't enough capacity, back to our slack space discussion, or there are too many simultaneous failures.
So the object is still accessible, but it's
naked. It no longer meets its protection policy. It's one more glitch away from data loss.
That's a critical distinction. Reduced availability is, I'm working on it. Degraded is, I can't fix this, I need a human.
And that human needs to act immediately. Good luck. It's a tough exam, but mastering these concepts makes you a much better specialist.
Thanks for joining us on this deep dive. We'll catch you on the next one.